every now and then people come up to me and they say, "Hey, you think it would be hard to build a railgun in my dorm room?" And I say, "Don't build a railgun in your dorm room. But if you were to build a railgun in your dorm room..." Okay, let me try this again.
Dumb ways to die. So many dumb ways to die. Dumb ways to die. So many dumb ways to die.
We will begin by preparing the electrolysis chamber water sample. This input to the system represents unclean water that is pumped from a local water source. For this experiment, we first prepared 1 liter of water and then another 500 milliliters to use when making a sodium hydroxide solution. Contrary to popular belief, the following is not a Breaking Bad episode. After a short ad placement, we prepared the scale to measure 60 grams of sodium hydroxide, more commonly known as lye. Using molecular conversions, we determined 60 grams of sodium hydroxide mixed in 1.5 liters of solvent results in a 1 molar concentration of sodium hydroxide solution within the electrolysis capsule. From previous testing of flow rate with the electrolysis subsystem, followed with research on these systems, we determined the higher the concentration of catalyst, the faster the reaction occurs, and the higher the output flow rate is. By pouring the sodium hydroxide solution into the chamber and thoroughly mixing, the solution is fully prepared. The next step is to screw in the chamber's conductive stainless steel plates.
And his name is John C.
These plates will not complete a circuit on their own. They only act as a medium to bring current into the solution. The solution and its added catalyst will complete the circuit and the reaction will begin. A bubbler and a check valve system is prepared to limit the damage a flashback can cause. Because of hydrogen and oxygen's fast flame rate, this system is necessary to prevent the flow of combusting gas back into the chamber. The bubbler is simply a secondary chamber filled with water to extinguish any flashback flames. The combustion chamber's gas needle is then prepared for ignition. After remembering the difference between red and black, the power supply was then hooked to both poles of the electrolysis chamber. In this prototype, our power supply is a 12-volt, 100 amp-hour car battery. Once the positive terminal is connected, the system is activated and ready to run. Hydrogen and oxygen gas do spontaneously turn back into water. However, to speed up this process, an igniter is used as the necessary activation energy needed to start this reaction. Once the torch is lit, the combustion chamber is screwed into place to capture the escaping steam generated by the torch. As the water molecules make contact with a cooler surface, they condense and form water droplets along the sides of the chamber. Given enough time, these droplets will collect at the bottom of the chamber, where they can be collected as clean water.
Is it too much to ask for a little precipitation?
This system successfully models the original aspects of our design, the electrolysis and combustion chamber. Other subsystems that are not modeled within this prototype, but are included in the full design, are the intake filtration system, energy system, and water storage system. We felt these systems didn't need to be tested, as they all exist as commonly used systems today. Now, why does this process work? Looking at the electrolysis capsule, we can see the cathode and anode, where reduction and oxidation occur respectively, are submerged in a sodium hydroxide solution. At the anode, 4 hydroxide ions are converted into 1 molecule of oxygen gas, 2 molecules of water, plus 4 free electrons. At the cathode, 4 water molecules plus 4 free electrons are converted into 2 hydrogen gas molecules plus 4 hydroxide ions. Canceling the hydroxide ions out on both sides, plus the 4 free electrons, and some reduction of the water, we are left with a net reaction of 2 water molecules for every 1 oxygen gas molecule and 2 hydrogen gas molecules. This is a non-spontaneous reaction where an electrical input of negative 1.23 volts at 1 molar concentration of sodium hydroxide is required, otherwise known as the cell potential. When looking at the combustion chamber, 2 molecules of hydrogen gas plus 1 molecule of oxygen gas are combusted to form 2 molecules of water. This is a spontaneous reaction with a cell potential of positive 1.23 volts.
1.21 gigawatts! 1.21 gigawatts! Great Scott!